Section 2.8 talks about implicit differentiation. We'd like to find the general derivative. We are so used to function notation, meaning f of x or y equal. If I was to say find a derivative for part A, students wouldn't have a hard time saying, well, dy dx equals derivative of x squared is 2x. That doesn't seem to be an issue. If I was to move the x to one side and say take a derivative, now it's kind of hazy. Now they're like, wait a minute. Can I solve for y? Yes, you could solve for y, but can you take a derivative of that function as is? The way you want to start thinking, I'm applying d dx to both sides. Whenever this matches, that's my traditional derivative. Whenever this doesn't match, I need to pick a d dx of that variable. So when I take a derivative of the right side is a 0, but derivative of the left side, since this is d with respect to x, so you're saying take d dx of y, because we don't know what y equals, minus 2x. And of course you could solve and get the same answer, because it's not like because you moved one variable to the other side it should be different. Or I could have moved everything to the right side, and when I take a derivative of the right side, that's a 0. When I take a derivative of this side, again it's d dx. Since that's not matching, the negative you ignore. That's d dx of y plus 2x. And you could move that over, and you get the same thing. And in general, if I have everything on one side, a constant on the other side, when I take a derivative of both sides, anything with a y will pick a d dx of that y, if that's the variable. If this is matching, keep in mind, we are taking d dx of x, but that's a 1. And the derivative here is 2x equal to 0, and of course you could solve for dy dx by saying that is 1 minus 2x. Now comes another part you've been doing. You just want to point it out so it gets easier as we do this. If I said take a derivative of those 4 functions, those 4 functions are identical in the sense, if I say take a derivative, well that's not implicit differentiation. That is the chain rule. I'm going to bring the power down, subtract 1 from the power, times the derivative of the inside. Now, I do want to point out, by the chain rule, that's the derivative of the inside. Here, well, you look at that, you say, wait a minute, that's a cubic as well, just like the previous problem. So, dy dx, and since that's an x, bring the power down, subtract 1 from the power, just like we did on the previous problem. Except, of course, the inside is a different story. It's a different function, so the derivative of that is 3x squared plus 2. Again, this is the derivative of the inside. So that's the chain rule. And if I look at the example G, again, dy dx, I've noticed, well, that is a cubic function. Bring the power down. So the first part of the problem is the same, times the derivative of the inside, which is 4x cubed. And that will be my answer. But now when I look at part H is part E, F, and G combined. And notice it's a function of x, not u. So I have 2 options. Option 1, I'll use u and y and use the chain rule like we did back in the days. Or I could say dy dx, so take d dx, dy dx, that's simple. Here, we're going to bring the power down because that's a power function. Subtract 1 from the power, just like we did on every single one of those. Now comes the tricky part. If I want to take a derivative of this, that doesn't match an x, and this is the function of x. Now, what's u? U could be x squared plus 3x. Then I would multiply by this. U could be x cubed plus 2x minus 1. Then I would multiply by this. And u could have been x to the fourth plus 1, and I would multiply by this. Since I don't know which of those is u, all what I'm going to say, since that doesn't match, whenever you tell me what u is, I'm going to multiply that. I'm going to multiply by that derivative. So, if you happen to be x squared plus 3x, I know what to do. If you happen to be x cubed plus 2x minus 1, I know what to do. And if you happen to be x to the fourth plus 1, I know what to do. And of course, you could be none of those. It could be a totally different function. So the idea is, whenever I take a derivative with respect to a variable that doesn't match, I'll pick a dx of that. Mainly we do ddx. So, and I know the derivative of y is simply dy dx. So when I look at the next example, now we're getting to non-functions. If I want to take a derivative of this, so d dx, well, the right side obviously is 0. That's simple. The left side, this is a power function. Remember, we're considering y to be a function of x. So, first we see the power, just like we did the previous problems. So you're treating this as if it's saying it's x squared plus 3x squared. Because you don't know what y is. It could be e, it could be f, it could be g. Well, don't you bring the power down, subtract 1 from the power? Times the derivative of the inside. Now the derivative of the inside, in this case, it's a y, but y is a function of x. So we're going to pick dy dx. And that's the implicit part. Plus, here we have the chain rule. Derivative of the first, that is a 1 times the second, plus the first derivative of y is dy dx. I do want to point out, when I said x times y, derivative of the first, you could have said d dx of the first times the second, but those cancel out and that's a 1. And here, bring the power down, subtract 1 from the power, and if you want to take a derivative of the inside, isn't the derivative of the inside d dx of x? That's a 1. So normally we don't write that. So you just have to adjust to this new way of doing the problem. I'm going to do this a different way for you, just to make sure you see it. Since I want dy dx, leave everything with dy dx on one side, and move everything else to the other side. So the other side will have a negative 2x and a minus y. And here I'll have 2y dy dx plus x dy dx. And since dy dx is common in both, I factor that. And dy dx would be, you would divide by that mess. You could factor a negative out of the top, but that wouldn't matter. It's the same thing. I do want to point out, there is I could show you a different way of doing this, in case you're having a hard time with this, but this is the most efficient way of doing the problem. So I'm going to go ahead and say, well, let's see. If I had y squared plus xy plus x squared equal 1. There is another way, and a student showed me this, and I really liked it, which is why I'm showing you this. A student said, you know what? When you want to take a derivative, take d. So what does that mean? That means when you take a derivative of anything, you're going to pick a d of that. So they said, okay, take a derivative of y squared, bring the power down, subtract 1 from the power, times d of y, plus the product rule. Take derivative of the first times the second, plus the first times derivative of the second, derivative of a power function, bring the power down, subtract 1 from the power, times the derivative of that x, and derivative of 1 is 0. Then they said, If you want dy dx, which is what we're asking, divide each of those by dx. And here you'll notice this will be y dy dx plus, that's a 1, plus x, that's dy dx, plus 2x, and that's a 1 equals 0, and we get exactly this. Now I'm going to do that on the next two problems as well. You should do something like that if you're having a hard time with this until you get the hang of it. So, again, the quick way of doing this problem is for you to say, well, I'm going to take d dx of both sides. That's going to be bring the power down, subtract 1 from the power. Since that's not an x, I'm going to pick a d dx of that, plus the product rule. Derivative of the first times the second, plus the first derivative of y cubed, bring the power down, subtract 1 from the power, times d dx of this, and derivative of x to the fourth, since that matches, is 4x cubed equals 0. Or, so this part I'm going to do on every problem, but the next few problems, take a derivative of this, you bring the power down, subtract 1 from the power, times d of y, plus, here the product rule, derivative of the first times the second, plus the first times derivative of the second. So, every time I take a derivative of a variable, I'll pick a d of that variable, bring the power down, subtract 1 from the power, times dx, and if I divide each of those by dx, I'll notice that matches, that's a 1, matches, and that's a 1. Either way, now you're going to have to leave dy dx on one side. Factor that out of those terms. So I'll have 4y cubed plus 3xy squared out of those two. And if I move those to the right side, I'll get 4x cubed minus y cubed, and dy dx would be 4x cubed minus y cubed divided by this parentheses, and factoring wouldn't get me anything, so hey, that's pretty good. Done deal. And if I get to the last problem, I'm going to take a derivative of this, so let me switch them. Let me start with this first. The product rule, derivative of the first, bring the power down, subtract 1 from the power dx times y cubed, plus x cubed times bring the power down, subtract 1 from the power dy, minus derivative of the first, bring the power down, subtract 1 from the power dx times y, plus x squared and dy, and derivative of this would be dx times y squared plus x times bring the power down, subtract 1 from the power dy equals 0. And divide everything by dx. So this is kind of longer. But it'll do the job. This is 3x squared y cubed plus 3x cubed y squared, and I'm going to call it y prime now, minus, and you could do that of course, 2x times y minus, because I'm distributing the negative, x squared y prime plus y squared plus x plus 2xy y prime equals 0. And now if I get all the y primes on one side, factor that out, I'll have 3x cubed y squared minus x squared plus 2xy. Hopefully I didn't make a mistake, and if I did, you get the idea. Move those to the other side. negative 3x squared y cubed plus 2xy minus y squared, and y prime or dy dx would be negative 3x squared y cubed plus 2xy minus y squared divided by that parentheses. Sometimes those simplify, most of the time they don't. And there it is. Now, we want to find an equation of the tangent. Well, we know how to do that. That's y minus y1 equals m into x minus x1. There. I need a derivative. Well, the derivative, if it's an x, that's 1 over twice the radical of x. Done deal. If it's a y, 1 over twice square root of y dy dx equals, and I should have moved that there. And when I take a derivative of this, that's going to be, well, 2 times derivative of the first times the second plus the first times derivative of the second. Now here it's your choice. You want to clean it up and get dy dx on one side. That's a lot of algebra. I could replace x by 1. That gives me a half plus, and y by 1, 1/2 dy. It's easier to deal with numbers than it is to deal with variables. 2 times 1 is 2, and 2 times, so there it is. Clear the fractions. Move this over and this over, and I'm looking at, what is that? 3y prime equaling negative 3. So y prime is negative 1, and that's the slope of the tangent, and done deal. And that would be my answer. And part B, I'm talking about, well, this is a circle. Again, it's not a function. I want to find the slope of the tangent at the point 1, 2. Well, it is y minus y1 equal m into x minus x1. There. What's the derivative? That's 2x plus 2y dy dx equals 0. Replace x by 1, that's a 2. Replace y by 2, that's a 4. So 4 dy dx is negative 2, and dy dx is negative 1/2. And there it is. And that's the equation of the tangent line. And that's pretty much it for this section.